Welcome to DES2 Unit 2 lecture on orthographic projection and advanced modeling review, multi-drawing standards by Todd Frazee. This lecture covers Chapter 10 in the Technical Graphics Communication text by Bertaline et al. References to page numbers may be found in the bottom left corner of each slide. Technical drawings are based on theory of projecting three-dimensional objects in two-dimensional media, such as paper drawings, or two-dimensional graphics, such as found in a 2D PDF document file. There are two primary concepts that are common between all projection theory drawing techniques. The first is the concept of line of sight, abbreviated as LOS. Line of sight is a concept of imaginary lines radiating between the viewer and an object. The second is the plane of projection, which is an imaginary flat plane upon which the LOS intersects to plot an image of the object. The image above displays objects viewed through the plane of projection. LOS lines intersect the plane of projection to define a 2D representation of the object in its given orientation. Each example is a different projection technique based on the orientation of the object in relationship to the plane of projection. Technical drawing is primarily grounded in two major projection theory types. The first type is perspective projection, where the object is viewed from a finite distance and LOS projection lines radiate from a single point. And the second type is parallel projection, where an object is viewed from an infinite distance and LOS projection lines are viewed from multiple points such that the lines are normal or perpendicular to the plane of projection. Perspective projection represents how the human eye perceives objects and their visual scale decreasing in size with distance. Perspective projection is an important projection technique for technical illustration to give the viewer a realistic pictorial image of how an object will look. Parallel projection represents graphically the actual size of an object. Parallel projection is the foundation for technical drafting and accurately describes the dimensions of an object to be made. Parallel projection is the technique that is focused on in this course. Orthographic projection is a parallel projection technique of LOS projected on a plane that is used to represent two dimensions of an object. In this example, to the right, we first view the object with the LOS lines projecting normal to the plane of projection. The LOS lines define features such as visible and hidden edges to produce a single two-dimensional view of the object. In this example shown, the orthographic view defines the two dimensions of height and width of the object. Multi-view drawings utilize orthographic projection techniques to represent an object with two or more orthographic views. The example shown on the right reflects the three commonly used views of front, top, right, side to describe the object. Three primary planes of projection are used in orthographic projection techniques. Frontal, which is typically parallel to the X and Y plane. horizontal, which is parallel to the X and Z plane, and profile, which is parallel to the YZ plane. If we revisit the example from orthographic projection, it is an example of frontal projection with the viewer observing the object with the frontal plane between them and the object to derive at the front view of the object. In this next example, the viewer is observing the object with the horizontal plane of projection between them and the object to derive at the top view of the object describing depth and width. In this last example, the viewer is observing the object with the profile plane of projection between them and the object to derive at the right side view of the object, describing the depth and height. Advantages of multi-view drawings. The advantage of multi-view drawings are that they are the most accurate description of three-dimensional objects, and each view represents the true size of the object in a two-dimensional format. There are two conventions used for the placement of views in orthographic projection. First angle projection, where the object is in between the viewer and the plane of projection. The view is projected as if the object face has been rotated and traced or imprinted on the plane. The second method of view placement is third angle projection, where the plane of projection is placed between the viewer and the object and projected onto the plane. In this course, we will be working in third angle projection, which is the method accepted in the United States. But be aware that if you are viewing a drawing that is not of domestic origin, some countries use the ISO standards for first angle projection. To verify the angle of projection on a drawing, look in the drawing title block for the symbol that depicts two views of a blunt cone. The corresponding symbols for the two different projection angles are shown on the right. There are 6 principal drawing views in orthographic projection that can be visualized as an object inside a 6-sided glass box. With third angle orthographic projection technique, the viewer moves around the box to see the object from each angle with the plane of projection between them and the object. The box is then unfolded to derive at 6 possible views as shown: front view, top view, right side view, left side view, rear view, and the bottom view. Typically, there are 3 views used on most drawings, which are the front, top, and right side views. However, the rule is to start with the front view and display the minimum number of views required to fully describe the object, which might not require the conventional 3 views. Regardless of how many views you determine you need to describe an object, observe the guidelines for the views to be proportioned to each other and equally spaced, as shown in the example on the right. There are 4 best practice steps for determining the orthographic views to select for describing a given object discussed on page 515 of the text. Step 1 is to determine the best position of the object. Step 2 is to define the front view, which will be the primary or central view all other views will be projected from. In my experience, this should be the view that can describe the highest number of dimensioned features. Step 3 is to determine the minimum number of views needed to completely describe the object. And step 4, once the front view is selected, determine the other views based on which will have the fewest number of hidden lines. Note that some companies avoid using hidden lines, which can increase the number of views required. ANSI Y14.2M defines standard conventions for lines used to depict orthographic views. The standard includes 11 basic line types with variations for a few of the line types. Some CAD software refer to the line types as line styles. Each of the line types in the standard have one of two line weights, or thicknesses, with thick lines measuring 0.6 millimeters wide and thin lines 0.3 millimeters wide, respectively. The line types defined by the standard can be thought of as an alphabet of lines for specific applications. We will go through each one, starting with the first three. The first line type is the center line. It can be used to represent symmetry, paths of motion, and mark the centers of circles and axes. Note the spacing requirements of the line elements in the image shown on the right. The second line type is breakout lines, or break lines, which are used to denote that an object has either been broken to reveal interior features, using a thick freeform drawn line as shown on the right, or show where an object has been broken to save drawing space, which is when the second example is used. Note the second style uses a thin line and observe the dimensional requirements denoted in the image. The third line type is for dimension and extension lines, which are represented by a solid thin line. Moving on to line types 4 through 6. The fourth line type is the section line, which is used to represent surfaces of an object sectioned by a cutting plane, and is represented by a solid thin line. The fifth type in the alphabet is the cutting plane line, which also has two variations, like the breakout lines, that are used to denote the locations of cutting planes used to define section views. The cutting plane line appears as a thick line with two dashes repeating every inch, or as a series of thick dashed lines as shown in the examples on the right. Note the strict dimensional requirements of the line elements. The sixth and final line type on this slide is the visible line, which occurs as a thick solid line to define the visible edges of the object depicted in the view. The visible line type is intended to be graphically the boldest line on the sheet, so the edges of the object are clearly differentiated from other line types. Next, we'll move on to the alphabet of lines 7 through 9. The seventh line type is the hidden line that represents features that can be projected in the view but not visible and occurs as a thin dashed line. With the element proportions detailed in the image to the right, these lines would only be seen by the viewer if the part were transparent. Line type number 8 is the phantom line, which represents movable features in different positions and occurs as shown on the right. The ninth line type is the stitch line, which can occur as a thin dashed or dotted line, as shown. This line type is specific to the soft goods industry such as fabrics and upholstery. The final two line types in the alphabet of lines are the chain line that occurs as a series of thick, short, and long dashes to denote an area that is to receive specific treatment, and the symmetry lines that are used as an axis for symmetry in a view. Symmetry lines are obsolete in the latest version of the standard that was recently adopted, but the line type is likely to appear on legacy drawings for many years to come, so it's important that you can recognize it. The next part of the chapter 10 covers representing holes and hole types. Hole features represented in specific ways based on type. Some hole features may include combinations of several of the following hole types. The first type I'd like to cover is called the blind hole. The blind hole is a hole that does not go all the way through the material and has a bottom. In views normal to the hole will be shown as a circle and typically will have the diameter and depth called in this view. In profile view, the depth of the full diameter will be represented as hidden lines, and if a drill point is allowed at the bottom, it will be project past as shown in the views on the right. The second hole type is the through hole. The through hole goes all the way through the material and exits on the opposite side. In views normal to the hole, the through hole will be shown as a circle and typically will have the diameter called out in the view. In profile view, the full diameter of the hole will be represented as hidden lines going through the part, as shown on the right. The third hole type is the threaded hole. The threaded hole can be either blind or through, but includes information to define the thread inside the hole. In views normal to the hole, the minor diameter of the thread will appear as a visible line circle, and the major diameter will occur as a hidden line circle. Typically, the diameter, thread pitch, and if applicable, the depth of the threaded hole are called in this view. In a profile view, the diameter of both the major and minor diameter will be represented as hidden lines as shown on the right. A fourth hole type is an end condition called a counterbore hole. The counterbore is a round flat bottom clearance pocket to recess a fastener head, such as a cap head machine screw. In views normal to the hole, the diameter of the counterbore will appear as a visible line circle that is larger than the related blind or through hole denoted in the view. Typically, the diameter and the depth will be called with specific symbols in this view. The example in the image to the right is calling out a 29 millimeter counterbore with a 14 millimeter depth. The profile view should detail the counterbore feature using hidden lines as shown in the image. The next hole type is also an end condition called a spot face, which is similar to the counterbore hole type. The spot face has a round flat bottom pocket to provide a clean flat landing for the fastener head to rest, but the depth is not critical and is typically shallow. In views normal to the hole, the diameter of the spot face will appear a visible line circle that is larger than the related blind or through hole denoted in the view. Typically, the diameter will be called with a counterbore symbol in the view, but the depth may be covered by a general note, a minimum depth, or not be called out at all. The example in the image on the right is calling out a 32 millimeter diameter spot face. The profile view should detail the spot face feature using hidden lines as shown in the image. The final hole type is also a hole in condition called the countersink, which is often confused with the counterbore hole type. The countersink is a round cone designed to match the taper on a flathead screw so that the flat screw head is nominally flush with the surface. In views normal to the hole, the diameter of the counterbore will appear visible as a visible line circle that is larger than the related blind or through hole denoted in the view. Typically, the major diameter and the taper angle of the countersink will be called with the specific V-shaped symbol in this view. The example in this image on the right is calling out a 29 millimeter diameter countersink with an 82-degree included taper angle. The profile view should detail the countersink feature using hidden lines as shown in the image. The next type of feature covered in the chapter are fillets and rounds. Fillets and rounds are similar features that most CAD software commonly simply label fillets, but there is a difference, especially if you are in a discussion with a tradesperson making parts for you. Fillets are interior corner radius features. The name is derived from a process of filling a corner with material to make an internal radius. Rounds are exterior corner radius features, and the term derives from rounding off the corners by removing material on a square edge with a tool. On drawings, fillets and rounds are depicted as shown in the image below each respective definition. Chamfers. Chamfers are similar to fillets and rounds, but are beveled corners that can occur as internal or external features. Chamfers are depicted on drawings as shown on the right and can be called out in a variety of ways that will be covered in a future lesson. The last and final symbol covered in the lesson is the finish mark. Finish marks denote surface finish or roughness requirements of an adjacent edge. They can occur in several styles and variations depending on the information they are intended to convey about the surface treatment. Please note the general shape and dimensional requirements so that you will recognize them in the future. More detail about finish marks may be covered in a future lesson. That's it for this lecture, and we'll catch you on the next one.